everyone, welcome back. Ready for another deep dive?
Always excited to dig into some fascinating research.
Well, get ready because today we're exploring solar variability and its impact on Earth. I've got a stack of scientific articles and reports here all about the sun. You know how it seems so constant and steady?
Right.
Turns out it's not. It actually fluctuates in its energy output.
Yeah, it's a bit more dynamic than most people think.
And those fluctuations have some pretty big consequences for us here on Earth.
Absolutely. Things like climate change, space weather, even our technology can be affected.
Okay, so let's start with the basics. This 1997 article, The Sun's Variable Radiation and Its Relevance for Earth, really lays it all out. It emphasizes that the sun's radiation isn't constant, but varies over time.
Over many different timescales, actually. We're talking minutes, hours, decades, centuries, even millennia.
Wow, so it's not just about the 11-year sunspot cycle we always hear about.
Nope, that's just one manifestation of this variability. There are shorter-term fluctuations like solar flares, and then these longer cycles that we can track through things like isotopes.
Okay, so why should we care about all this? What's the relevance of these solar variations?
Well, for one thing, if we want to understand climate change, we need to know how much of it is natural, driven by the sun, and how much is due to human activity.
Right, so separating out the natural fluctuations from the human-caused ones. That makes sense.
Exactly. And then there's the impact on our technology, satellites, communication systems. Anything in space is vulnerable to sudden bursts of solar energy.
Right, I've heard about solar storms knocking out power grids and stuff.
That's a real concern. A strong solar flare could fry sensitive electronics or disrupt communication signals. It's a big deal, especially as we become more reliant on technology.
So we've got the sun's radiation varying over time, and we know that matters. But how does that actually affect Earth's atmosphere? This 1997 article mentions some patterns there.
Yeah, researchers have found that cycles in Earth's atmosphere actually mirror the sun's activity cycles. And this connection gets stronger the higher you go in the atmosphere.
So the sun's variability is kind of leaving its fingerprints all over our atmosphere.
Pretty much. The upper layers, like the thermosphere, are more directly exposed to solar radiation, so the effects are more pronounced.
Makes sense. But what about surface temperatures here on the ground? Is there a direct link between solar variability and the temperature we feel?
That's where it gets a bit more complicated. There's definitely a connection, but it's not as straightforward. You have to factor in all the other things that influence Earth's temperature too. Natural climate cycles, volcanic eruptions, greenhouse gases. It's a complex system.
So untangling all those influences to see the sun's specific impact is tough.
It's a challenge for sure. Scientists are still working on it. But one thing this 1997 article points out is that the sun is currently in a period of unusually high activity compared to the past few centuries.
Interesting. I wonder what the later research has to say about that.
Yeah, it'll be interesting to see how that trend is played out.
Okay, well, let's fast forward a bit to this 2003 report, The Sun to the Earth and Beyond, a decadal research strategy in solar and space physics. This one is a bit different. It's not just research findings, but a sort of roadmap for future research in the field.
Right, it's a panel of experts outlining their priorities for the next decade of solar and space physics research.
And one thing that jumps out at me is their emphasis on space-based research. They talk about needing advanced technology to propel spacecraft to the outer reaches of our solar system.
Absolutely. To really understand the sun, we need to get a closer look. They recommend developing things like solar sails and space nuclear power to get us there.
Imagine the data we could gather with a probe orbiting Jupiter, or even closer to the sun.
The possibilities are pretty mind-blowing. But even without those missions, there's still a lot we can learn with the tools we have now. This report digs into the sun's magnetic dynamo, the engine that drives all its activity.
Right, like the heart of the sun.
Exactly. And it's fascinating how these magnetic fields erupt through the surface, creating sunspots and those incredible coronal structures.
Yeah, those pictures are always amazing. But we still don't fully understand how those processes work, right? Like how CMEs, flares, the solar wind, all that stuff gets accelerated.
There are definitely still mysteries there. We're learning more all the time, especially with things like the Advanced Technology Solar Telescope, which allows us to study the sun's magnetic field in incredible detail.
It sounds like we need more deep dives.
Always. But maybe for now, let's shift gears a little and talk about the practical effects of solar variability. how it impacts technology and society here on Earth.
Right, because it's not all just theoretical, right? We've all heard about the potential for solar storms to mess with power grids and communication.
Yeah, that's a major concern. This 2003 report really stresses that. Severe space weather events could disrupt communication systems, knock out GPS, cause widespread power outages, even damage spacecraft.
That's kind of scary when you think about it.
It is. And that's why they call for translating research into practical applications, especially for agencies like NOAA and the Department of Defense, who are responsible for space weather forecasting and preparedness.
So it's not just about understanding the science, but also about protecting ourselves.
Exactly. We need to be prepared for the sun's next big outburst, just like we prepare for hurricanes and earthquakes.
Makes sense. Okay, so we've covered a lot of ground already, but there's still plenty more to explore. We've got some groundbreaking research from 2024 to discuss. This study, Magnetic Diffusion in the Solar Atmosphere Produces Measurable Electric Fields, reports the first direct observation of electric fields associated with magnetic diffusion in the sun.
That's huge. It was long thought that measuring those electric fields was nearly impossible because they disappear so quickly.
So how did they manage to do it?
It was thanks to the Daniel K. Inouye Solar Telescope, the most powerful solar telescope ever built. They used it to observe an event called an Ellerman bomb, sort of a mini explosion on the sun, and they were able to capture those elusive electric fields.
Wow, that's impressive. What does that tell us about the sun's activity?
Well, it provides evidence that magnetic diffusion is important for releasing energy in these events. The better we understand those processes, the better we can predict solar flares and improve space weather forecasts.
So it's like we're getting a clearer picture of the sun's engine at work.
Exactly.
Yeah.
And that's crucial for understanding its impact on us here on Earth.
This is getting really fascinating. I'm excited to see what else we uncover.
It's a game changer for sure. Now, this next 2024 article is about something called slip running reconnection.
Ooh, that sounds complicated.
It is, but I'll try to explain it simply. Basically, it's how magnetic field lines in the sun's atmosphere reconnect in really complex ways. And that leads to these super fast movements and energy release.
So like imagine a tangled mess of ropes suddenly snapping and rearranging, releasing bursts of energy.
Yeah, that's a good way to visualize it. So in this study, observation of superalvenic slippage of reconnecting magnetic field lines on the sun, they actually observed this happening.
Oh, wow. So they saw those magnetic field lines in action.
Well, not directly the lines themselves, but they saw evidence of what's called superalvenic slippage of flare kernels.
Yeah.
These are like super concentrated regions of energy during a flare.
Okay, so they're moving really fast.
Super fast. Faster than the speed of magnetic waves in the sun's corona.
Wow, like supersonic jets, but in the solar atmosphere.
Exactly. And this is a big deal because it confirms a theoretical prediction that had been around for a while but never actually observed.
So it's like a missing piece of the puzzle.
Yep, it gives us a clearer picture of how these energetic events on the sun actually unfold. And they use data from the interface region, imaging, spectrograph, IRIS, to make these observations.
Another one of those high-tech instruments giving us a closer look at the sun.
Exactly. We've talked a lot about the sun itself, but I'm curious about its influence on other celestial bodies. Like, does solar variability affect asteroids or other planets?
Yeah, that's a good question. I mean, the sun's gravity holds the whole solar system together, right? So there's got to be some effect.
Absolutely. The sun's influence reaches far beyond Earth. Take this 2024 article, Constraints on Fifth Forces and Ultralight Dark Matter, from OSIRIS-REx Target Asteroid Bennu.
Whoa, hold on. Asteroid tracking and dark matter. How are those two things connected?
Okay, so picture this. By carefully tracking the trajectory of asteroid Bennu, scientists can look for any tiny deviations from its expected path.
Okay, I'm following so far.
And those tiny deviations could be caused by the gravitational influence of something we can't see, like dark matter, or maybe even a hypothetical fifth force beyond the four fundamental forces we know.
So they're using the asteroid as a kind of test particle to probe the unseen forces at play.
Exactly. It's pretty ingenious. And while this study didn't actually find evidence for a fifth force, it helped set new limits on its strength and range, which is still valuable information.
Right. It helps narrow down the possibilities. It's amazing how studying one thing, like an asteroid, can lead to insights into something completely different, like dark matter.
That's the beauty of science. It's all connected. Speaking of connections, let's circle back to the sun's magnetic dynamo. Remember, we talked about that earlier.
Yeah, the engine driving the sun's activity.
Right. This 2023 article dives into the different mechanisms that scientists think are involved in that dynamo. It's called evaluating solar-like behavior in turbulent alpha and Babcock-Layton mechanisms, using non-kinematic, non-linear flux transport solar dynamos.
Whoa, that's a mouthful.
Yeah, the title's a bit intimidating. But basically, they're using computer simulations to compare two main theories about the sun's dynamo. One is the turbulent alpha mechanism, the other is the Babcock-Layton mechanism.
Okay, so they're like competing explanations.
Yeah, sort of. And the researchers found that the turbulent alpha dynamo was much better at reproducing certain features of solar activity that we observe in the real world.
Like what kind of features?
Specifically, the grand solar minimum and maximum periods, those extended periods of either really high or really low solar activity that have happened throughout history.
Oh, right. I've heard about those. So the turbulent alpha dynamo seems to be a better fit for explaining those.
Exactly, which means it might play a more important role in the sun's long-term cycles. And that's crucial for predicting future solar activity.
Right, which affects our understanding of things like climate change and space weather, so it's not just theoretical, it has practical implications.
Absolutely. This kind of research helps us build more accurate and reliable models for forecasting what the sun might do in the future.
So it's like we're building a better weather map for the sun.
That's a great way to put it. The more we know, the better we can prepare.
Okay, let's dive into another 2024 article. This one, Magnetic Diffusion in Solar Atmosphere Produces Measurable Electric Fields, highlights a really exciting discovery. The first direct observation of electric fields associated with magnetic diffusion in the sun.
I know, right? For years, scientists thought these electric fields were almost impossible to measure because they just dissipate so quickly.
So what changed? How did they finally manage to observe them?
It was all thanks to the Daniel K. Inouye Solar Telescope, which, as we've said, is the most powerful solar telescope ever built. It allowed researchers to capture these super short-lived electric fields during a solar event.
Which event?
They were looking at something called an Ellerman bomb, which is like a mini explosion on the sun's surface.
Ah, okay, so they saw these electric fields happening during these mini explosions.
Exactly. And that's important because it tells us that magnetic diffusion, the process of magnetic fields spreading out and dissipating, is a key player in these energetic events.
So we're seeing the sun's engine in action, converting magnetic energy into heat and light.
Yep, that's a good way to think about it.
Yeah.
And the more we understand about these processes, the better we can predict things like solar flares and improve our space weather forecasts.
It's like we're peeling back the layers of the sun and getting a closer look at its inner workings.
Exactly. Every new study adds another piece to the puzzle, giving us a more complete picture of this incredible star.
Now, remember that idea we discussed earlier, slip-running reconnection, where magnetic field lines reconnect in all these complex ways, leading to those rapid movements and bursts of energy?
Yeah, I remember. It's a pretty mind-bending concept.
Well, there's another 2024 article, Observation of Super-Alfvénic Slippage of Reconnecting Magnetic Field Lines on the Sun, that delves even deeper into this phenomenon.
Interesting. What did they find?
They were observing flare kernels, those bright, concentrated regions of energy that get released during a solar flare. And what they saw was that these kernels were actually exhibiting something called super-Alfvénic slippage.
Super-Alfvénic slippage? What does that even mean?
Basically, it means they were moving faster than the speed of magnetic waves in the sun's corona.
Wow, so incredibly fast. Like watching a cosmic speed race happening right on the sun's surface.
That's one way to put it. And this observation is really significant because it provides crucial evidence to support a theoretical prediction that, until now, had never been directly observed.
So it's like another confirmation that our understanding of these complex processes is on the right track.
Exactly, and it highlights how important it is to combine theoretical models with real observational data. That's how we build a more complete and accurate picture of what's happening on the sun.
It's a beautiful interplay between theory and observation. They inform and enrich each other, leading us closer to the truth.
And who knows what other groundbreaking discoveries await us as our observational technology continues to improve.
It really is amazing. And thinking about all these new discoveries, it makes me appreciate how much our understanding of the sun has grown, even just looking back at that 1997 article we started with.
It's true, the sun's variable radiation and its relevance for Earth, it almost feels like a different era of solar science now.
It does, doesn't it? Back then, scientists were still debating whether the sun's output was even truly constant.
And now we know it fluctuates on all these timescales, some we hadn't even considered back then.
Yeah, from minutes to millennia. It's incredible to think about the range of those variations and how they all matter.
And as we've seen, those fluctuations have these big implications for us here on Earth. Climate, technology, even our safety in space. It's amazing how something so far away can have such a direct impact.
It is, isn't it? It really underscores the interconnectedness of everything in the universe, and it highlights how far we've come in terms of our scientific understanding.
From basic sunspot observations to building these complex models of the sun's magnetic dynamo.
It's a real testament to all the researchers who have dedicated their lives to studying the sun. But of course, there's still so much we don't know.
That's the thing about science, isn't it? Every answer leads to more questions.
Exactly. Like, we still haven't figured out exactly how the sun's magnetic field is generated.
Or how it interacts with the solar wind.
Right, those are some of the big mysteries that solar physicists are still grappling with.
It seems like solving them is going to require this multifaceted approach, using observations from space telescopes, ground-based telescopes, even lab experiments, and those supercomputer simulations.
It's a big puzzle, and we need all the pieces to fit it together. And that 2003 report we discussed really emphasized the importance of international collaboration for this kind of research.
Yeah, the sun to the Earth and beyond, it made a strong case for sharing resources and expertise across borders.
Because the sun affects everyone on Earth,
Yeah.
right? Understanding its behavior is a global concern.
Exactly. It's a reminder that science really transcends borders.
It's a shared pursuit of knowledge. And when we collaborate, we can achieve so much more. We look at the advancements in observational technology we've been discussing. The Daniel K. Inouye Solar Telescope, for example.
Right, that's a product of international collaboration, and the data it's producing is incredible.
It's like having this giant magnifying glass on the sun, allowing us to see these tiny details we could never observe before.
And then there's the Interface Region Imaging Spectrograph, IRIS.
IRIS is amazing. It's focused on the chromosphere, that layer of the sun's atmosphere where so much of the energy transfer happens.
It's like watching the sun breathe, seeing how that energy flows from its core outwards.
It's truly remarkable, and to think we've come so far in our quest to understand this star, from simple observations to really probing the heart of its engine.
And every new discovery opens up more avenues to explore. So after this deep dive, what stands out to you the most?
I think what really hits me is the interconnectedness of it all. The sun seems so far away, but it's woven into every aspect of our existence.
I know what you mean. Its energy gives us life, its magnetic field protects us, and its variability affects everything from our climate to our technology.
And yet we often take it for granted. It's a powerful reminder that we need to keep studying and understanding the sun, not just for the sake of knowledge, but for our own well-being.
Right, it's about safeguarding our future. The more reliant we become on technology, the more vulnerable we are to space weather.
Exactly. Improving our forecasting and developing mitigation strategies is crucial.
And that's going to require continued collaboration, research, and this drive to unravel the sun's mysteries.
Absolutely. And as we look to the future, one thing's for sure, the sun is going to keep surprising us.
I have no doubt. Well, this deep dive has been incredibly enlightening. It's amazing how much we've learned from just a few articles and reports.
It's a testament to the power of focused exploration and open-minded discussion.
So until our next deep dive, keep looking up, keep asking questions, and keep exploring the wonders of the universe.